Oh my gosh, Gabby's here. Yay. Okay, so let's get started. We're going to talk about work, potential energy, and power. And I'm going to stop my video. Oh, Portia. Wow, nice. Did I get her? Yeah. Okay, so this is all about potential energy, kinetic energy. There's a little bit of work. I'm not so sure about the power part. I think that's for next time, but let's look and see. I can't ever remember. Okay, so a force pushes a box. Wow, yay. It's really exciting, guys. There's a lot of people here. Okay, so the force that we just saw pushed the box, right? And it pushed it for a short distance, and that causes the box to start moving. So if you kind of think about something in motion tends to stay in motion as long as you give it that little start and there's no friction. So what we're going to talk about is that force gives an object energy, and that energy means that it's going to do some work. So energy is the ability to use force and move something a distance. So the main thing that you want to know is that energy is the ability to do work. Okay, so if a force F is used to move an object a certain distance, then the force does work on the object. So if I move this just this distance, then what I have is work. Force times distance is work. And that's pretty important. Now think about this. What is a force? Anybody? Write it down there in the chat box. What is a force? Gravity is a force. The force of gravity. Okay, what else? That's good. It's a push or a pull on an object. Friction would be considered probably a pull because if you're pushing something, it's pulling backwards, right? And I guess if you're pulling something, it's holding you back. So, um, okay, strength or energy. Okay, all right. So you guys, all of these are good. Now I want you to tell me, give me that formula. How about the formula for force? What is that formula? Let's get more, there you go. Second law, Newton's second law. What is that? Yeah. So force is mass times acceleration. And if you think about your weight, what is that acceleration? You guys already wrote that down there. That acceleration is gravity, right? That's how you find your weight. So um, force is mass times acceleration, multiplying that distance too. All right. So the units for work are newtons. And then the units for, the units for force are newtons. The units for distance is meter, which means that the unit for work is a newton meter. All right? But the more common unit is called a joule. So 1 joule is equal to 1 newton meter. 1 joule is defined as the amount of work for 1 newton of force to move an object 1 meter. Okay, it's just the big definition, but basically what you have to remember is that when you do work on something, it is called a joule. Oops, sorry. So energy comes in many forms, but the basic definition of energy is in terms of work. So we all have a concept of work, right? Everybody thinks about work in a different way, but in physics, the definition is very precise. Work is done when a force moves a body through a distance, and it's defined as force times distance. Now, I want you guys to think about something. When you pick up a book, okay? Think about picking up a book, it's on the table, you pick it up. Did you do work on that book? Okay, so everyone is saying yes, you did work on the book, and that's right, because you picked it up, so that was the force, and you moved it a distance, vertical distance, but you moved it a distance. Now, think about this, you have that book in your hand, and you walk across the room. Are you still doing work on that book? No, this is a definite answer. It's a definite yes or no answer. Are you still doing work on that book? Okay, the answer, guys, this is kind of a tricky question, but the answer is actually no. You're not doing any more work on the book because you picked it up a distance and now it's staying that same distance and you still have the same force, so you're doing no more work. As you carry it across the room, you're doing no more work on that book. All right?
But aren't you?
Nope.
Because you're moving it. So
You're moving. You're moving, but the book itself is still in place. It hasn't gone up or down, unless, of course, you move it up or down. But if it's still in the same place as you're carrying it across the room, you're not doing any more work on that book.
Okay.
Okay? The book is just there. You're just carrying it. You're doing work on yourself, you're moving yourself, but you're doing no more work on that book because you're not pushing or pulling that book. Does that make sense to everybody? Yes, no, maybe? Okay, good. It's kind of a trick kind of question, but it's fun. All right, so let's think about this. A weightlifter in the video, we don't have the video, but we're pretending we're watching this video. He lifts a 280 kilogram weight, a distance of 0.75 meters. So how much work does he do during one lift? So he's just going to lift it one time. How much work is he going to do? Guys, write it down there. If you don't have a calculator, just write down what you would do. Remember what the definition of work is. It is force times distance. Think about this now. Do you have a force here? Do you have a mass? What do you have? What are you going to do first in order to do this problem? I'm going to give you a minute. If I don't see anybody typing, I'm going to hit next and we'll see. Okay. No, that's a good answer. Now it's a good answer. Okay, so let's look. There is a force needed to lift the barbell, guys. There it is. All right, and it's got to be equal to its weight. Do we have a weight up here? What do we have? This is not a weight, this is a mass. Mass is not the same as weight. Remember, weight is mass times gravity. So we need to multiply that mass by gravity to get the force. Does that make sense to everybody? Yes, no, smiley face? Maybe? Okay. Now that we have a force, how would I find the work that needs to be done to lift this barbell just one time? What would I do now? guys remember? I don't have my pen, so this would be, I'm not even going to attempt to write with my mouse. Okay, Naomi is typing, so Tay is typing. Okay, so all these people in this class, and these are the only two that are going to attempt. Yay, I like the attempts. Okay, so they're right. We have to multiply it by that distance that they're going to move it, right? So it's 2,744 times 0.75. And so it's, for those of you that don't have a calculator, it's 2,058 joules. All right, sounds good, right? Now we know the force, right? What if he lifts it twice? What has he doubled? Has he doubled his force? Has he doubled the mass? The distance, right. Tay is here, so he said the word. So I heard him. Keep typing. Right. He's doubled the distance. So what now do you think, how much work is he going to have to do to lift this? Oh, there's the video. I didn't even see that.
I had the answer. I lost it.
Oh no. Okay, we got somebody typing. Oh my gosh. Jamie, the question is right here. If he lifts this bar 2 times, okay, how much work is he going to do? Okay. We got somebody answering. Yulissa, I can't say her name. That's so sad. I'm going to work on that. Wouldn't it be math if he were lifting it twice? No, if you're lifting it twice, you're lifting it one time 0.75 and then you bring it back down, right? And when you bring it back down, the weight is actually doing work on you. Does that make sense? Because it's pushing down on you. You push up, it pushes down.
So you're like adding gravity to yourself?
Yeah.
Okay.
And then the second time you push it up, right? It's going up. So we're not going to double the force. It still takes the same amount of force, but we're doubling the distance. So, yay, good job. Okay. Does that make sense? I want everyone to say yes or no here. And if it does not make sense, okay, good job. Now we're going to talk a little more about work. It's a product of force and distance, right? This is the equation. If work is done on an object, its energy is changed. So if we are lifting a ball, it has a mass of 2 kilograms. What is the weight of this ball? Has a mass of 2 kilograms. What's the weight? Right, mass times gravity. And you know what? For simplistic sake, what we're going to do is we're just going to say that gravity is 10. Because it makes it easier to multiply in your head, because I know not everyone has a calculator. So what's the weight of this ball? Yeah, or, okay. If we just call it 10, it's easier to multiply. Okay, 19.6, 20 is good. All right, so what's the force? What force must be used to lift this ball? Same thing, right? 20 or 19.6. The weight of the ball or the weight of whatever is the force that it takes to lift something up.
So force and weight is the same thing. Okay,
Yes.
that's what it was confusing.
Okay, good. Light bulb. You can almost go home today. Okay. So, how much work will be done to lift this ball a height of 5 meters? And again, think about it as 20, the force is 20 instead of 19.6, so that you can do it pretty easy in your head. Mhm. Okay, so, wow, Naomi, what do you, wow. Not sure, what did you multiply, Naomi? If you're using a calculator, maybe you forgot to clear something. That's what I'm thinking. Okay, so 100. And again, instead of using the 19.6, if you use the 20, it's easier to multiply in your head. So it's going to take work, or 100 joules, to lift this ball 5 meters. Now, since 100 joules of work is done on the ball, its energy was increased by 100 joules. This was added in the form of potential energy. Potential energy. Yeah, that's what I thought. Is the energy stored in an object due to its position? All right, and it is stored by doing work. So our ball, its position is its height, and it's 5 meters above the ground. So this form of potential energy is technically called gravitational potential energy. So one of the things that I kind of want you to think about is whenever you walk up a mountain, or when you go hiking and you walk up to those 14ers. I've never done one, so I don't know. But I like hiking. That's a little strenuous for me. But anyway, anytime that if you were standing on a table, you would have potential energy, gravitational potential energy. And that energy is due to the fact that you are, I don't know, 3 or 4 feet off the floor. Does that?
Like spaceships, like coming back down from the moon, like they start like catching on fire because they're having more energy
They're actually,
in the atmosphere.
once you go up, you have your gravitational potential energy, and then on your way down, you change that to kinetic energy. So they're releasing stuff. But yeah, it's sort of the same situation. Okay. So gravitational potential energy is found by multiplying the mass of an object by the gravity and then the height. So mass times gravity is going to be the weight times the height. All right, and here is the formula. Okay? So there's formulas that you should be writing down on a formula sheet. Number one is work for this particular section. The other one is force. You need to make sure that you write down mass times acceleration, or mass times gravity. And then potential energy, mgh. Okay, so for this particular case, 2 is the mass, 9.8, but we use 10, and then times 9, oh, that should be 5. I thought I changed that. Times 5, and you're going to get 98, or 100 if you use the 10. Okay, so now with the ball up 5 meters off the ground, it has 100 joules of potential energy stored in it. Now it has the ability to do that much work. All right, so here we go. Whoa.
So work and potential energy is like the same or no?
Sort of like the same thing. The only thing is that when you do work, you're just moving something vertically. But if you move it horizontally, I did that wrong. You're moving something horizontally, but if you move it vertically, that's potential energy, gravitational potential energy. Okay, so the question, just real quick, it was a good question. Work and potential energy are kind of the same thing, but potential energy always has to do with moving something vertically, okay?
So potential energy will only come in play if something's going up and down.
Up or down, exactly right. So potential energy only comes into play, and again, I just want to tell you what he's saying because they're good questions. It only comes into play when you're moving something up and down, all right? If you're moving something horizontally, that's going to be work, and that kind of work is going to be kinetic energy, and we'll see that in a couple minutes. Okay, so if we have a ball and we roll it up a ramp, it reaches a height of 5 meters, it still has the same potential energy. It just, we didn't do it straight up, right? We pushed it up. So there's an advantage to rolling it up a ramp instead of picking it straight up if it were something that was really heavy, right? Think about a piano. If you had to move a piano, would you want to pick it straight up or push it up a ramp? Probably push it up a ramp.
I'll pick it up a little faster.
It is faster to pick it up. However, you know, you don't always have that much strength.
Yeah.
Okay, so what about this? What about this situation? A 2 kilogram ball is rolled up a ramp until it reaches the height of 5 meters. It's a different situation here. We're going a little ways this way and then straight up. What do you think? What's the potential energy? Anybody? Anybody? Use 10 as gravity. Same thing. Same thing. Just because you're moving it in a different situation, it doesn't make the potential energy any different. You're still moving it a height of 5 meters. Okay.
Because it was I did that.
Yeah. So when you're calculating potential energy of any object, all you need to know is the mass and the height of the object because the gravity is always going to be 9.8 or 10 if you want to make things a little easier.
So acceleration wouldn't matter.
Not how fast you moved it up. Mm-mm. So how the object gets there to the height, it doesn't matter. How, you know, if you want to get it 10 meters up, it doesn't matter. You're still going that ball or whatever object is that you're moving is still going to have that amount of potential energy. Okay? No matter what path, it's still going to have the 98 joules. All right. So, when you lift a ball to a certain height, you do work on it. The work is equal to the weight of the ball times the height. So work and potential energy are going to be the same. All right? They're the same number, but they have different meanings. Potential energy is always has to do with height. Work can be height, it can be distance. Does that make sense to everybody? Okay. All right. So now it has potential energy stored in it. This means the ball has the potential to do work. Oops. There we go. But before it can do work, it must convert that potential energy into another form, and that's called kinetic energy or the energy of motion. And it changes all of its potential energy when it falls to kinetic energy, which is energy of motion. And the thing you can think about is like with a roller coaster, or if you, I don't know if anybody skateboards, but
Yes.
when you go up the side and you're at the top, you're full of potential energy. When you go down to the very bottom and not back up, but down at the bottom, all your energy now is kinetic. So potential, kinetic.
But technically, like if you're holding the ball up, wouldn't your arm have the potential energy and not the ball?
No, because you did work on the ball to get it up there.
But so y'all don't have any potential
Mm-mm.
energy.
No, you did work on the ball to move it up there. Okay, so another good question. If you were holding a ball and you just pushed it up, or you still had it in your hand and you were holding it up, however high you can hold it up, your arm doesn't have the energy. You pushed the ball up, so the ball has all the potential energy. Okay? All right. Good questions. So kinetic energy is the energy of motion. And the equation for kinetic energy is, if that ever stops, 1/2 the mass times velocity squared. So kinetic energy, energy of motion, depends on the moving object's mass and the square of its velocity. That's what the 2 up there means, squared. So it's the velocity squared. So, ready? We have a kinetic, find the kinetic energy of a 5,000 kilogram Asian elephant running 4 meters per second. This would be a little bit hard. So what's half of 5,000? 2,500, right? Good. And so we did the 1/2 the mass. And what's 4 squared? 4 times 4, 16. So it's 2,500 times 16, and I don't have a calculator on me right now. So half of the mass, we were right, 2,500. Velocity squared is 16. So the amount of work that this elephant is doing, and it's not potential work because he's running horizontally, right? He's doing 40,000 joules of work. All right, good, Cassie. Yes. And it is all kinetic energy. And again, it is joules because mass is kilograms, velocity is meters per second squared, and that's the same thing as joules. All right, so how could you increase his kinetic energy? How could you increase this elephant's kinetic energy? Think about it. Okay, we've got one answer over here that says make it run faster. Anybody else? I guess if it weighed less, it could run faster. but
I think it would, I would just like bring down the kinetic energy though.
actually, it would if it's still running at 4 meters per second. More weight. Okay, we got more weight. We got some, um, with food, you know what? That's not a bad answer because you get more energy and it's in the form of chemical energy, right? Once you eat food, it's released as chemical energy. But to increase its mass would also increase the kinetic energy. But if you increased its speed, that would make it increase faster. Does that make sense? Because the speed is squared. So you're going to, a square of a number gets bigger faster. Does that make sense to everybody? Do you guys remember that from, I don't know, algebra? Okay. So if you want to increase your kinetic energy, run faster. All right. You don't have to weigh less. You don't have to weigh more. Just run faster. All righty, guys. So what if we double its mass? So instead of 5,000, it's going to be 10,000. Remember, that is our formula. And I know you guys probably don't have calculators. So 1/2, 5, or 10,000, we're doubling its mass, is 5,000. He's still running at 4 meters per second. So now it's 5,000 times 16. Can anybody do that in their head? 80,000. Nice. Oh. Nice. 80,000. Good. So does that make sense? We doubled its mass. So what we got here is 80,000. And if you notice, that doubled the kinetic energy. Now, what would its kinetic energy be if its speed doubled? So instead of going 4,000, and it still has a 5,000 mass, but instead of going 4 meters per second, it's going 8. Again, remember, this is our formula. Where did it go here? This is our formula. Mass is still going to be 5,000, but now instead of going 4, we're going to go 8. It's 8 times 8. I don't know. I don't do it in my head. I don't.
Yeah, that's it. That's what I got.
Okay. Come on, guys. Quick, I need another answer. Just one more. Anybody, anybody. You can do it, Jamie. You can do it. Okay, let's see. Okay, but now instead of doubling, hold on, what am I saying? There we go. Instead of doubling the mass, we're doubling the velocity. If I double the velocity, that's going to make my kinetic energy 4 times as much because the velocity is squared. Okay? All right, and Tay got the answer. Okay, nice, good job. All right, so does that make sense as far as this kinetic energy? Make sure that you know this formula also. Work, force times distance, potential energy. Somebody type it in there. If you used a calculator, that's not cheating. What is potential energy? What's the formula? Let's go. Can't leave until you type it in. We will stay here all day. I got one. Come on, guys. And the other one you have to type in before we can leave, and it's right before your eyes, kinetic energy.
Oh, that's how you do squared.
Yeah, it's the little caret above the 6. That's okay. I know what you meant. Come on, Gabby. Lexi. Yolisa. I'm not saying your name right. I'm going to go out there and have Mr. Horton help me with that. All right. So all you guys, if you have any questions, stick around. If not, you can leave except for Gabby, Lexi, Yulisa. Everyone else gave me potential energy and kinetic. And that was the, huh?
How do airplanes work? That's not a real question.
Airplanes?
Yeah.
That's going to be whenever we get into, oh, I don't even know if we get into that. But we get into airflow because they work the way the wings are designed. The air that flows over the wings helps them to stay afloat, kind of like birds. the air, they push down, but the air pushes back up because they don't really.
Yeah, because I seen one time I seen a bird like the wind was blowing really hard. It was trying to land, but it was getting pushed back.
Right. Yeah.
I never seen that before.
Okay, guys. If you have no questions, we are good to go. And Gabby and Yulisa. All right. Have a great weekend.